I'm Angel Ramos. This is the introduction of the work, the outline of the work. First, I will introduce two main topics we are trying to join here. From one side, we have shape memory alloys, and on the other side, we have RFID. Next, I will present the theory and the design of our sensors, theory of time-coded ultra-wideband RFID, which is the technology we are using, and the topology we have designed. Next, I will present the results, and finally, we will draw the conclusion. As with the previous speaker said, RFID is a widely extended technology used in logistics, medicine, or industry. It consists, of course, in a reader retrieving information of one or more tags using a wireless link. And one of the main interests recently is to add sensing capabilities, to have smart tags instead of just identification. Also, we want battery-free wireless sensors for long-term applications. Even though we could put batteries, there are some applications where we cannot afford to just last them for 5 or 10 years. We want even more than that. And there is other type of applications, for instance, hazardous environments. I'm talking about explosive atmospheres or place with flammable gases. In this case, we can't even afford to put a battery. So here, Chipless RFID comes as an alternative. As the previous speaker said, it consists on physical permanent modifications on a scattering antenna. They can be time or frequency coded. And the good thing about Chipless is that we don't need not even battery, but not even electronics. We don't need a chip inside the tag. So we don't need supercapacitors to store energy, and the risk for this type of environments is minimum. Of course, Chipless RFID sensor tags, they are very simple and inexpensive because it's just a scattering antenna with physical modifications. The read range is very short compared to chip-based. We don't have a digital communication scheme. And the ID space is also short. But for some applications, they have lower accuracy, but for some applications such as alarms or thresholds, this is enough. Also, moreover, ultra-wideband has gained greatest interest in the recent years because the American FCC and the European ETSI regulated it by 2002. So it consists on using sub-nanosecond pulses, which in frequency translate to a bandwidth from 3.1 to 10.6 gigahertz. The good thing of ultra-wideband, due to its huge wideband, is it is good against multipath. It is barely affected by narrowband interferers like Wi-Fi or Bluetooth. It has a high range resolution and penetration in material. And the other important thing is that since we work in time and we work with delays, localization of the tags is easy compared to RSSI approaches. Also, as I said, there is another main topic in this work. Are the shape memory alloys. These alloys are alloys of two metals, which the form depending on the temperature. One of the most famous one is nickel titanium, or commonly called nitinol. It's often used in dental products, for instance, in brackets or this type of products. And the main principle is that we heat up this alloy and we change its shape while it's heat. Then, if we cool it down, the shape is some kind of memorized or stored by the material. If we change the shape when the material is cooled down and we heat up the material again, the material by itself will deform to the stored shape. So, based on this principle, we want to develop a thermal threshold detector using a chipless ultra-wideband RFID tag. This is the principle of operation of our system. What we have is a bi-static reader with two antennas, which sends a pulse to a tag. The pulse hits the tag, and we receive the backscattered reflection. In the receiver, we have mainly two peaks. The first peak, we call it the structural mode, is the part of the pulse which just hits the tag shape. Depends on the shape and the size and the material of the tag. It does not depend on the fact that the tag is designed to transmit a radio frequency signal. And the other peak we obtain in the receiver is the tag mode. The tag mode is depends on the load at the end of the antenna. We can see here we have a scattering antenna with a transmission line. It's the pulse which enters the antenna, travels the transmission line, and then is backscattered towards the reader again. Normally, we code the ID in the delay between these two modes, and this delay depends on the length of the transmission line. We can see here some equations. I won't go into detail. Basically, we model the antenna as a two-port scattering network, and in the receiver, we see the structural and tag modes as a sum of both terms. As we can see here, the tag mode is delayed depending on the length of the transmission line, and the reflection coefficient of the tag mode depends on the load on the antenna. The idea here is that the nitinol switch will change this reflection coefficient by connecting a switch. We can see it here. It's a copper sheet which connects the transmission line to a short circuit in option A. We can see on the top. We connect the beginning of the transmission line to a short circuit. This is option A. Or option B, we connect the end of the transmission line to a 50 ohm load. So in the first case, we would have the same tag mode, but since the peak is so overlapped with the structural mode, because we don't have a delay to separate both modes, practically we disable the tag mode. With option B, we also disable the tag mode, but what we do is we connect it to a 50 ohm load. So instead of having an open circuit, we have a matched load, and all of the energy of the tag mode, which is traveling inside of the tag, is absorbed by the load, and we don't have a reflection. The tag is shown here in the photograph. Is fabricated on an RF substrate. As for the nitinol goes, it's from Kellogg's research. Here is a working diagram. It's more or less what I explained. We heat up the nitinol wire over the transition temperature range, and we deform it to the final position, which is disconnected. Then we cool it down, and we connect the copper sheet and the nitinol. Then, when the temperature of the nitinol is above body temperature, 37 degrees, this nitinol alloy, what it does is, as I said, it deforms again to the initial position, which would be disconnected. We can see here both photograph for both states. This is the initial state. It is connected, so we don't have a tag mode. And when the nitinol reaches a temperature above the threshold, it disconnects and enables the tag mode. As for the reader, we use a low-cost radar from time domain. It sends a pulse from 3.1 to 5.6 gigahertz. It is inside of the of the ultra wideband band for regulation. It is much lower cost than vector network analyzers, which are commonly used in Chipless RFID. And we have measured this at 50 centimeters, but it could be measured up to about 2 meters with this type of tags. Of course, this distance is much lower than the distance we were talking just a moment in the previous talk, but we have to keep in mind that this doesn't have a chip and is the simplest approach. As for this as the results, prior to showing the results, I will talk about the processing techniques we apply. The first technique is time windowing or gating. Since we have the reader antennas very close to each other and the tag is at a longer distance, we can filter the coupling contribution, which is the peak which goes from the readers transmitting to its own receiving antenna. We can filter it in time domain by shifting the window. The second technique is the background subtraction. What we do is we measure the scene where the tag is going to be placed before placing the tag. So we subtract then this scene from the actual measurement with tag in order to eliminate clutter and other contributions or reflections in the floor and other environment which are not actually the peaks due to the tag. And the final technique we apply is the continuous wavelet transform. It can be seen as a multi-scale filter or correlator, and this is shown here in this reference in detail. But this technique has proven to be very useful for this type of tags. These are the measurements. This is the unprocessed signal. We can see here that we have a huge coupling contribution at the beginning of the window. And then if we zoom inside, we see the structural and tag modes. But we cannot actually see a very big difference between the threshold surpassed or no threshold surpassed. So if we apply background subtraction, we can see here that the structural and tag modes can be seen. And if we apply on top of this the continuous wavelet transform, we can see that we obtain the two peaks we were willing to obtain. The first peak is the structural mode, and the second peak is the tag mode. For the threshold surpassed option, of course, is the same with both approaches, because when the copper is disconnected, we have exactly the same tag. So to conclude this talk, we have presented a threshold temperature detector. We're using Chipless time-coded RFID tags. It's very low cost compared to other approaches, and the reader is also low cost. It's a commercial radar. The temperature threshold is at body temperature, 37 degrees, but it could be changed by changing the composition percentage of nickel and titanium. But this is, of course, dependent on the manufacturer of the nitinol. And finally, we have localization possibilities because we are using a time domain ultra wideband approach. And this would be all. Thank you for your attention.